once we've done vertical asymptotes, the next thing to look at are horizontal asymptotes. And this is sort of more generally going to be, for us, this is essentially a version of end behavior for our rational functions. And so it's going to have that same kind of like multiple case breakdown, and the different cases are going to depend on both the degree of the polynomials. So in this case now we have sort of a numerator and a denominator polynomial, so we have like two different polynomials working together, right? So our sort of like form f of x, right, is supposed to be like p of x over q of x, and if I kind of write this out as generic polynomials for both of them, this is going to seem like an enormous long expanded thing. I'm going to try to write as short a version as I can, right, but this sort of expanded polynomial form with our coefficients and our constants, right? So we'd have maybe kind of, you know, an A version up top and then a B version maybe on the bottom. And I'll use n for our variable up top, and then we'll use m on the bottom. And in theory, right, these could go a lot of different ways. And so what we're really going to be focusing on is, you know, the same sort of general idea with our polynomials, was that as we get bigger and bigger and bigger values into it, as we get further and further out to the left and the right, what really determines what the graph does, what the function does, is going to be both the degree and the leading coefficient on that. Well, and both of those ideas come from the leading term. So what's really going to matter here is we're really just going to look at the two leading terms. So we're going to consider the leading terms from the top and the bottom only. So the results here are really only going to depend on what the relationship is between, you know, essentially the degree on the top and the bottom, which is going to be the powers on the biggest x's, and then what the relationship is in some senses between the two coefficients. So let's break it down with the three cases. So case number one. So let's do, what should we do? Let's do the degree is bigger on top. Let's do degree in the numerator, which is top, is bigger. That is the end behavior that's sort of closest. That sort of matches most closely the sort of end behavior that we had for our regular polynomials, which is just that we're going to get no asymptote, no horizontal asymptote, I should say. What we're going to get is, so end behavior is the curve heads towards positive or negative infinity. So we're just going to get some sort of shooting off to infinity. We'll have to sort of check in a little more detail whether we get a positive or a negative number. We'll go through that in detail when we do our sketches. Case number two is going to be, well, what if they are imbalanced? What if they have the same degree? Divide this up. So the degree is the same. what happens there, if the degree for each of your polynomials is the same, you're going to get a horizontal asymptote at y equals whatever the fraction is you get from the two coefficients. In some sense, what's happening here is if, let's say you have an x to the 5 and then this is also an x to the 5. Well, in some sense, as you get further and further out, those are the things that are going to make a difference. And if the sort of size of the x's is balanced, x to the fifth over x to the fifth, those things are also going to balance each other out. And what's going to really, the only thing that has an impact is what the numbers are here. So is this a 2x to the 5 over a negative 7x to the 5, in which case what you would get is a horizontal asymptote and like a leveling out towards whatever that fraction is. So it's going to be the two leading coefficients over top of each other. So you're going to get this horizontal line, y equals whatever these the fraction is you get from the coefficients. So 2 over negative 7, like I said before. We'll do a couple examples so you can see a few different things. Case number 3 is maybe the sort of most clear. So save our sort of best for last here in some sense. And so that's if the degree in the numerator, again, which is our top value, is smaller. So if the degree up top is smaller, if we have, an x cubed on top versus an x to the 4 or an x to the 5 on the bottom, what that means is as the numbers get bigger and bigger and bigger, what happens is the polynomial on the bottom actually grows faster, right? You have more x's on the bottom, so the bottom grows faster and faster and faster than what's on top, and it kind of forces the whole graph to head towards 0. You're going to get a horizontal asymptote at y equals 0. So you sort of either get this sort of plus minus infinity, which is kind of what we were dealing with before, in which case you don't have a horizontal asymptote, or you get a horizontal asymptote that's sort of based on a fraction of your coefficients, or you get in case 3, if you have a smaller degree up top, you just get a horizontal asymptote at 0. Let me give you sort of 3 kind of quick cases with sort of similar functions to illustrate this. So let's say example number 1, f of x is 3x to the 4 minus 2x squared over 6x cubed minus 3x to the 2. I'm just going to keep these guys short. So our end behavior, so it's going to be based on the two leading coefficients. We're really sort of just looking at, the two leading terms. So 3x to the 4 over 6x cubed, right? This is sort of obviously a bigger numerator term, right? The 4 is bigger than the 3. So this is going to be no horizontal asymptote. We're just going to have sort of end behavior that's some version of positive negative infinity, and we'll obviously sort of go through how to determine which of those two things is happening when we do our graphs here in some of the upcoming videos. If I do g of x, let me take that exact same setup, but let me flip the top and the bottom. So let's do 6x cubed up top and then 3x to the 4 minus 2x squared on the bottom. So now what's happening, right, is I'm really looking at 6x cubed over 3x to the 4. So now, right, our bottom degree is larger, and so what we're going to do is get horizontal asymptote at y equals 0. So that's going to mean that this graph, as we go out to the edges, is flattening out, and it's heading towards 0. I'm not really drawing any sketches for these yet. Again, we'll sort of do the sketches and the visualization here coming up when we sort of put it all together. Our third case would be then, what if these guys were sort of stacked equal to each other? We'll do a quick one, H. Let's kind of keep these numbers together. I'm going to do similar to G. I'm just going to adjust 3x cubed minus 2x squared. So I'm just going to adjust a little bit that 1 degree to sort of get these two in sync. So now they're the same, right? So 6x cubed over 3x cubed. You can see pretty quickly, right? Here the powers are the same, so we're going to have a horizontal asymptote at, so y equals, so just based on the coefficient, so in this case 6 over 3, that's really just 2, right? So horizontal asymptote at y equals 2. So we're going to have a leveling out of this graph, but it's going to be up at the y value 2. So it's up away from the axis a little bit, but it's still going to have this sort of flattening out kind of behavior. Again, only as we get like out to the edges. All of our sort of ups and downs and these other like asymptotes and this, the holes and the x-intercepts, all that stuff is still sort of happening here in the middle. So that's our sort of test and our setup cases for horizontal asymptotes.